Okay, next example here is example 2, which is to find the area bounded by the region enclosed by these three graphs. So first step here is to just graph everything. So I'll go ahead and draw our axis system. So there's the x-axis. So square root of x looks like this. So there we go. And we can give them function names if you want to, or we can even just say square root of x, whatever. X squared is a parabola. So since it's a parabola, it does continue on this side as well. So there's both sides of the parabola. And then we have x equals 2. So x equals 2 So x equals 2, we have to think, where are we going to draw? X equals 2 is a vertical line. So because these two graphs intersect, it does actually matter where we place it, right? I mean, if I'm drawing this picture not specifically to scale, but we at least want it to be accurate in a certain sense. So if I were to draw the vertical line x equals 2 here, that's fine. And if I move it over a small amount to the right, that would also be fine, because this region that it's creating is still the same kind of region. But because these intersect, it is going to matter, do I draw my vertical line over here? That's a very different region than if I draw it through the intersection point. And it's also a very different region if I strike it over here. So we should first figure out what this point of intersection is. We can do the algebra, but it's easier to just think. What number, when you square it, gives you the same answer as when you take the square root of it? Well, there's only two solutions. 0 squared is 0, and the square root of 0 is also 0. So 0 is a solution. And also, 1 squared is 1, and square root of 1 is 1. So 1 is also a solution. You could actually just set up the equation and go from there, although that tends to be a little bit more of a pain, I think. Because then you have to do all this nice factoring, which isn't bad. It's just, to me, I think, kind of annoying. So you can do it that way as well. Okay, so if this is 1, then that means our vertical line should go someplace over here. Okay. All right. So really, this quadratic should go up further to make my region. So how about I redraw this slightly? I'm only going to draw part of my parabola, since we know we're not going to need the other half. I'm also going to move my line down a little bit just to make it a little bit easier to draw, that's all. There we go. Okay. So there we go. There's our parabola. So there's x squared, here's x equals 2. Just tried to make our little region here a little bit easier to see. So this is the region whose area we're looking for. Okay. So this region here looks like we are going to integrate from whatever this, we found this value out, that's x equals 1. So this picture is not, this graph is certainly not drawn to scale, but if I were going to draw this to scale, this parabola would shoot way above the page. So you just kind of have to bear with me there. If you want to, we can sort of pull this out and look at it that way if you'd like. There we go. That's sort of what we have. So this curve is x squared. This bottom boundary is square root of x. And this vertical line boundary on the right is x equals 2. And this point here happens to be at x equals 1. Okay, so that looks like a nice little setup there. So for us, we should be able to read this off pretty easily. The area between them is from 1 to 2, top function minus bottom function. So 1/3 x cubed minus, this would be x to the 3/2 divided by that, so 2/3 times that, between 1 and 2. So 8/3 minus 2/3 square root of 8 minus 1/3 plus 2/3. And it looks like that simplifies not so great, but if you spend a little bit of time doing some arithmetic and some algebra here, you can make it look like 9 minus 4 root 2 over 3. All of these expressions here I spent time figuring out many years ago when I wrote these notes initially. So don't worry if you don't have this answer written down. This is an acceptable answer as well. Hopefully you would take the time to, at the very least, combine your like terms. So yeah. Okay.